This is the beginning of Chapter 5. Chapter 5 is about rational expressions, rational equations, and rational functions. It is a chapter with much content. As you see, there are 8 sections to it, and I won't read them all to you, but we will go through them one by one. And so the first section, 5.1, is about rational expressions and functions. And we will be doing the 3 basic operations: multiplication, division, and simplifying, as we would with rational numbers. So as you will see, rational expressions and rational numbers have much in common. And so the objectives of section 5.1 is to find all numbers for which rational expression is not defined. And that should sound somewhat familiar because we have done this before. And state the domain of the function, and then multiplying rational expressions by 1 using an expression like a divided by a. And then we are going to simplify rational expressions, and then we're going to multiply rational expressions, and last but not least we'll be dividing rational expressions. What's critical about all of these things is that you do lots of examples. I will be doing some, but I really leave it up to you to look in the book, section 5.1 in particular, and make sure you get the basics right. Section 5.1 is very foundational, and so there's a lot of new things that you learn, and it's important that you provide some depth of this experience by doing as many examples as you possibly can to make sure you understand everything about any of the topics that I mentioned here among the objectives that we'll be discussing. First of all, let's define a rational expression. It's simply a quotient of 2 polynomials, where the one in the denominator, of course, has to be non-zero, because otherwise it wouldn't be defined. So here's officially an expression that consists of the quotient of 2 polynomials, but the polynomial in the denominator is non-zero. It's called a rational expression. And here are some examples: 7 divided by 8, z divided by -6, a divided by b, etc. And some that are more complicated, where you have polynomials in the numerator and denominator. So, and again, you have seen these type of expressions before when we talked about functions, and they in some cases look like this. And so the first exercise, find the domain of f if f of x equals x squared minus 4x plus 9 divided by 2x plus 5, and then write both set building notation and interval notation for the answer. You may remember that these type of functions are defined for all values of x, except for those for which the denominator is equal to 0. And so remember how we found out for which value or values of x the denominator is equal to 0? Well, we take the denominator, in this case 2x plus 5, and set it equal to 0. So 2x plus 5 equals 0, and solve for x, so that x equals minus 5 divided by 2. So for all real numbers other than x equals minus 5 divided by 2, this function is defined. And also remember, if the numerator is equal to 0, that's no problem, because then the function is simply equal to 0. But so we're always concerned about the denominator. So in set building notation, we write the solution as follows: the set of all x such that x is a real number and x is not equal to minus 5 divided by 2. And in interval notation, it would be the interval from minus infinity to minus 5/2, with a parenthesis, union the interval from minus 5/2 to positive infinity. And remember, infinity always gets a parenthesis. And that is the answer. The second exercise is very similar. Here the question is, find the domain of g if g of t equals t squared minus 9 divided by t squared minus 7t plus 10. And as before, to find out for which the denominator is equal to 0, we set the denominator equal to 0. And so we want to find out for which values of t squared minus 7t plus 10, for which values of t is equal to 0. So this, of course, is a quadratic equation. And one way we know how to solve quadratic equations is by factoring. So when we factor this, this would be t minus 2 times t minus 5 is equal to 0. And that is, now we use the zero product principle, and that is our property. That is, we set each factor equal to 0 and solve for t. So when t minus 2, we set that equal to 0, then t is equal to 2. And when t minus 5 is equal to 0, then t equals 5. So for these values of t, the denominator will be equal to 0. So therefore, we must exclude that from the domain of the function. And when we put it in set builder notation, we write it as a set of all t such that t is a real number. It's a real number. And where t is not equal to 2 and t is not equal to 5. In interval notation, it would be the interval from minus infinity to 2 union the interval from 2 to 5 union times union interval from 5 to positive infinity. So what this does, it's the interval from minus infinity to plus infinity, but it leaves out t equals 2 and t equals 5. To find equivalent rational expressions, let's talk about how to multiply rational expressions. So if a divided by b is a rational expression, we multiply it by the rational expression c divided by d. That's equal to a times c divided by b times d, which looks very familiar in terms of fractions of real numbers. And so the same applies when we have rational expressions. So let's look at an example. Here's example number 4. And so what we want to do here is this would be our a divided by b times c divided by d. So that's simply 2x squared minus y times 3x plus 2 all divided by 3x plus 4 times 3x plus 2. And these expressions are equivalent because 3x plus 2 divided by 3x plus 2 is equal to 1. And we know that any number, including rational expressions multiplied by 1, is the same expression. So multiplying anything by 1 gives us back whatever we multiplied with. And then the same thing for exercise number 7. So here we multiply minus 1 times 2a minus 5 in the numerator, and minus 1 times a minus b in the denominator. So minus 1 times 2a is minus 2a, and minus 1 times minus 5 is positive 5. And so minus 1 times a is minus a, and minus 1 times minus b is plus b. Or we can switch these terms around to begin with a positive term. 5 minus 2a divided by b minus a. So either way it works, it's fine. You can leave it this way or that way. Mathematically, these two expressions, of course, are equivalent. And the greatest common factor in the numerator is 3. So we have 2a plus 3 divided by 3. And then the 3's cancel. So it would be equal to 2a plus 3 divided by 1, which is equal to 2a plus 3. The 1 comes from cancelling the 3 against the 3. You don't necessarily have to use this step in between. I just did it for clarification, so that you might, in case you're wondering whatever happened to the 3. So the 3 against the 3 is a 1. Let's talk about canceling. Canceling is a shortcut that you may have used for removing a factor of 1 when working with fraction notation or rational expressions. But you got to be careful. So it's possible to speed up your work. Canceling can be done for removing factors of 1 only in products. So the key word here is products. It cannot be done in sums or when adding expressions together. And so our really valid concern is that canceling be done with care and understanding. So we're going to look at this example here. But here's what I've seen in many cases, and that people look at an expression and it looks like x minus y divided by x, and then people cancel the x against the x, which is exactly what you cannot do. And here's the reason why. X is not a factor. X is a term of a sum. And you say, well, it doesn't look like a sum. Well, I can write this as x plus negative y. Now, it's really a sum, right? So you can never cancel this x against that x. Like in the previous example, we factored a 3, and so we canceled the 3, and that's why that worked. Remember, the example was 6a plus 9 divided by 3. So here we factor out a 3 times 2a plus 3 divided by 3, and now we could cancel these two 3's to become a 1, etc. You saw the previous example. So be really careful when you cancel something, that you only cancel factors, never ever terms of a sum. It doesn't matter how good it looks, you cannot do it. Even if you have an expression maybe like x plus 1 divided by x minus 1. It looks like you should be able to cancel the x's. Again, the reason why you cannot do it is because every x is a term of a sum. And that's why you cannot cancel them. Okay? And the ones don't cancel either. So, in other words, this is a prime polynomial, that's a prime polynomial, they're different, and that's as far as we can go. The following example shows you how it's done properly. And so you look at the expression, or the rational expression, 9x squared plus 6xy minus 3y squared divided by 12x squared minus 12y squared. So what's happening here, first of all, a greatest common factor of 3 is factored out in the numerator. Then the polynomial was factored into x plus y plus 3x minus y. In the denominator, a 12 was factored, and it was split up into 3 times 4, so the 3's cancel. And then the x squared minus y squared was factored into x plus y times x minus y. Now we can cancel x plus y against the x plus y, but 3x minus y and x minus y remain the way it is, and there's just another factor of 4. And so this is no longer, this cannot be reduced anymore. You cannot cancel anything. So what we're really removing here was a factor of 3 times x plus y divided by 3 times x plus y, which is equal to 1. So let's do another example like it, and that is the number 12 here. We have 2y squared plus 6y plus 4 divided by y squared minus 1. So the idea here is to factor the numerator and to factor the denominator. So we notice there's a greatest common factor of 2 in the numerator. By factoring it out, we get 2 times y squared plus 3y plus 2. And the denominator looks like y squared minus 1 squared. And so now we can factor the numerator and denominator some more. We have the 2, and y squared plus 3y plus 2 factors into y plus 1 times y plus 2. And we know the denominator is a difference of 2 squares, so that is y plus 1 times y minus 1. And now we can cancel the y plus 1 factors. And so then the answer is 2 times y plus 2, 2 times y plus 2 divided by y minus 1. And we typically leave the numerator, and in some cases when that's appropriate, the denominator also in factored forms. In other words, we don't necessarily multiply this out. So then the answer to this question was, or to this exercise, is 2 times y plus 2, 2 times y plus 2 divided by y minus 1. For number 16, we see number 13 rather, we see that we can factor out 20. So 20 times a squared minus 4b squared. And in the denominator, we can factor out a 16. So 16 times a squared minus 4ab plus 4b squared. And that's equal to 20. And we realize that this is the difference of 2 squared, a squared minus 2b parentheses squared. So this would be 20 times a plus 2b times a minus 2b. In the denominator we have 16, and this factors into a minus 2b times a minus 2b, or a minus 2b squared, so a minus 2b. So we don't write it out as a minus 2b squared because we want to be able to cancel if possible, and we are able to factor to cancel these two factors. And 20 divided by 16 is equal to 5/4. So 5 divided by 4 times a plus 2b times a plus 2b divided by 4 times a minus 2b. Oops, minus 2b. So it looks like we could cancel something here, but again, as I mentioned before, the a's are terms of a sum, and so is the 2b and the minus 2b. So this is it. This is the final answer. So let's write it down here. So 5 times a plus 2b divided by 4 times a minus 2b. Let's look at number 14, the guided solution. So here we have y minus 3 divided by 3 minus y. So we leave the numerator the way it is, but from the denominator we factor out a -1 or simply minus. So that then becomes a y minus 3, parentheses. So now we have 1 times y minus 3. So we're making the numerator a factor, y minus 3 times 1. And in the denominator we have minus 1 times y minus 3. So now we can cancel the y minus 3's in the numerator and denominator. So that becomes then a 1. And this minus 1 comes from 1 divided by minus 1. And 1 divided by minus 1 is minus 1. And minus 1 times 1 is minus 1. So that's then the final answer to this quotient here. Y minus 3 divided by 3 minus y is equal to minus 1. You may want to rethink this one here. Let's do number 15. So p minus q divided by q minus p. So p minus q divided by q minus p. And so in the numerator, we can write it as 1 times p minus q, just factor out a 1. In the denominator, we factor out a minus 1. And so this becomes p minus q also. And now we can cancel the factors p minus q against the p minus q. And we have 1 divided by minus 1, which is equal to minus 1. So the answer to this question, to this problem here, is -1. Number 16 is somewhat similar. T plus 8, we can factor out a 1. Again, 1 times t plus 8. And in the denominator, we can factor out a -1. We get a t plus 8. Now we can cancel the t plus 8. And we get 1 divided by -1. And that is equal to -1. So that would be the answer to number 16, -1. And notice that the answer is independent of the variables. It's always equal to -1 when you have expressions like this or like that. The answer is -1. One of the key observations of multiplying rational expressions is that we simplify them before we multiply. So let's look at number 17 and see what that's all about. So when we look at number 17, we can see that x minus y to the third power simply means x minus y times x minus y times x minus y times And from the second expression here, we can factor out a 3 times x plus y. So 3 times x plus y means we factor the 3 here, greatest common factor. Then in the denominator, we have an x plus y. And here we have x squared minus y squared, the difference of two squares. And we know that that factors into x plus y times x minus y. I guess I made it a little bit too long here. So now let's see what we can cancel here. So we can cancel the x plus y against the x plus y, and the x minus y against the x minus y. So then our answer is 3 times x minus y times x minus y, these two factors here, divided by x plus y, the only factor left in the denominator. So here we can then write the answer. X minus y times x minus y divided by x plus y. When we look at number 18, we notice that a to the third plus b to the third is the sum of two cubes, and it factors into a plus b times a squared minus ab plus b squared. So that's the equivalent of a to the third plus b to the third. Then a squared minus 2ab plus b squared, that's a perfect square. It's an a minus b times a minus b, or a minus b squared, a minus b times a minus b. And then in the denominator, a squared minus b squared is the difference of two squares, and it would be a plus b times a minus b. And then this term here cannot be factored. That's simply a squared minus ab plus b squared. Now let's look at some terms. For some terms we can cancel, and so we can cancel the a plus b against the factor a plus b, and we can cancel a squared minus ab plus b squared against this factor a squared minus ab plus b squared, and then we can cancel the a minus b against the a minus b, and what remains is simply a minus b. So in other words, the answer here is a minus b. So what this means is that you have to remember a few things about factoring, and that of course is what we did a lot of in the previous chapter, and here you have an opportunity now to apply these kind of skills. Before we get into dividing and simplifying, let's talk about reciprocals. And you may remember that two expressions are reciprocals of each other if their product is 1. And to find the reciprocal of a rational expression, we simply interchange the numerator and the denominator. Find the reciprocal of x plus 3 divided by x minus 5. Well, the reciprocal is x minus 5 divided by x plus 3. We simply exchange numerator and denominator. So, what about number 20, x plus 7? Well, we can certainly write x plus 7 as x plus 7 divided by 1. Now we have an explicit numerator and a denominator. So now we exchange that, so it would be then 1 divided by x plus 7. That would be the reciprocal of x plus 7. So it's reciprocal for number 19, and that's a reciprocal for number 20. And for number 21, I apologize, I should have moved it up further. Okay, so x plus 7, we write as x plus 7 divided by 1. Now we have a numerator and a denominator, we exchange them. Here's our reciprocal, 1 divided by x plus 7. This one here is quite simple. We simply exchange numerator and denominator. So this then becomes y to the third minus 9 divided by 1, which of course we write as y to the third minus 9. Now let's divide rational expressions. And so here's the general instructions how to do that. To divide by a rational expression, multiply by its reciprocal. And again, that's what we learned in probably middle school. How do you divide a fraction by a fraction? You multiply the first fraction by the reciprocal of the second fraction. So we do it the same way with rational expressions. If a, b, and c and d are rational expressions, then a divided by b divided by c divided by d is equal to a divided by b times the reciprocal of the second expression, d divided by c, which would then be ad times bc. And then factor and simplify if possible. Again, this is very much the same as what we learned about fractions. So divide and simplify. Here's a guided solution to that. So here we have the expression x squared plus 7x plus 10 divided by 2x minus 4 divided by x squared minus 3x minus 10 divided by x minus 2. So we leave the first expression the way it is, x squared plus 7x plus 10 divided by 2x minus 4. And then we have the x minus 2 now becomes the numerator for the reciprocal, x minus 2. And now we need to factor as much as possible. And so that we notice that the first trinomial, x squared plus 7x plus 10, factors into x plus 5 times x plus 2. And then here we have an x minus 2 already. And then in the denominator, we factor out a 2, and we get a 2 times x minus 2. And then we factor this expression, x squared minus 3x minus 10, into x minus 5 times x plus 2. Now we can cancel a number of factors. We can cancel the x minus 2 against the x minus 2 and the x plus 2 against the x plus 2. And what remains is the x plus 5 this factor here divided by 2 times x minus 5. And again, as tempting as it may look to cancel the x and the 5s, don't do it because these are terms of a sum. And remember, we can only cancel factors. So don't ever make that mistake. To do number 23, we have a squared minus b squared, our first rational expression, divided by ab. And now we multiply by the reciprocal of the second expression, so we now use the denominator, make it the numerator, 2a squared b squared divided by a squared minus 2ab plus b squared equals. Now again, we realize that a squared minus b squared is the difference of 2 squares, and so we know that that factors into a plus b times a minus b divided by a times b. And so here we have 2 times a squared b squared, or 2 times ab times ab, We're just going to rewrite a squared b squared as ab times ab. And the denominator here, that's a perfect square. That is a minus b squared, or a minus b times a minus b. Now we're looking for factors to cancel. And we can certainly cancel the a minus b against the a minus b, and the ab against this ab. So what is remaining is 2ab times a plus b in the numerator, and in the denominator we have a minus b. So that is the answer for number 23. So let's write down the answer. It is 2ab times a plus b divided by a minus b. So I wrote the answer next to the original problem statement. So when we're looking at number 24, we have an a to the third plus 8 divided by a minus 2 divided by parentheses a squared minus 2a plus 4 times a minus 2 quantity squared divided by 1. So now we multiply by the reciprocal of the second expression. So that is, we have a to the third plus 8 divided by a minus 2 times 1 divided by a squared minus 2a plus 4 times a minus 2 squared. So now we want to start factoring certain expressions. First of all, a to the third plus 8 is the same as a to the third plus 2 to the third divided by a minus 2. Times 1, so we can leave out the 1. In the denominator we have a squared minus 2a plus 4. And this we write as a minus 2 times a minus 2. Now, here we have the difference of 2 cubes. So let's write that in factored form. So then the numerator becomes a plus 2 times a squared minus 2 times a. So minus 2a plus 2 to the second power, or 4. So that's a to the third plus 2 to the third in factored form. And now for the denominator we have a minus 2 times a squared minus 2a plus 4 times a minus 2 times a minus 2. Let me retrace a couple of steps. There's times a minus 2 parentheses squared. So that means 1 times a minus 2 parentheses squared in the numerator. So that means a to the third plus 2 to the third times a minus 2 times a minus 2. And then when we factor a to the third plus 2 to the third, it becomes a plus 2 times a squared minus 2a plus 4 times a minus 2 times a minus 2. And in the denominator we have a minus 2 times a squared minus 2a plus 4. So what we now have is we can cancel the a squared plus minus 2a plus 4 against the a squared minus 2a plus 4, and the a minus 2 against the a minus 2. And so what remains then is an a plus 2 times an a minus 2. So it's a plus 2 times a minus 2. Okay? And by the way, one way to prove to yourself that you're correct about this is you can simply substitute some numbers for a and b. What I recommend is do not substitute 1 and 1 or 1 and 2, but maybe like 2 or a equals 2, b equals 3, and then you'll see that the original statement for number 24, would come out correct for a select a value for a like number 2. In the end, it comes out correctly to, well, a equals 2 would not be a good example because then the denominator would be 0. So maybe select a equals 3 and see how that works out. Okay? Anyway, that's the final answer. Let's write that down. So that's a plus 2 rather, times a minus 2. Who knew that such a complicated expression is equivalent to a very simple expression here in number 24. This concludes section 5.1.